Hi everyone, good morning. I hope you guys had a wonderful weekend. So let's start on Chapter 11, Intermolecular Forces. So states of matter, so this is your solid, liquid, and gas and stuff. Just so you guys know, solids and liquids are called condensed phases, but all this other stuff is basically review. You guys should know that gases are really far apart and they're moving really fast, and a solid, they're very organized, and they're just kind of vibrating in place. Now, the state that something is in, whether it's a solid, liquid, or gas, depends on two things. So the first is how much energy they have, right? So if they don't have a whole lot of energy, they're going to be in a solid phase. If they have a lot of energy, they'll be in a gas phase. And the second is the strength of the attractions between the particles. This is intermolecular forces. Without intermolecular forces, solids and liquids would not exist. Now, there's a difference between intramolecular forces and intermolecular forces. An intramolecular force is a bond. So this is your metallic, covalent, ionic bonds. Okay, that's an intramolecular attraction or force. Okay, those are always going to be stronger than any intermolecular forces. Okay, because in an intermolecular force, they're just attracted to each other. They're not actually sharing electrons or transferring electrons. It's just a partial charge attraction. So intermolecular forces, we call them van der Waals forces. So that's the general term for dipole-dipole, hydrogen bonding, and London dispersion forces. And we're going to talk about all of those like individually. And then all of those influence a lot of properties. So when you talk about, let's see, melting or boiling point, viscosity is just how thick a liquid is, and then vapor pressure, so the pressure of a vapor above a liquid. All of those things are dependent on intermolecular forces. The first one we're going to talk about, though, is an ion-dipole attraction. This isn't a van der Waals force, and this is a little different than anything that we've talked about. And maybe you didn't even see this in honors last year, but it's between an ion and a polar molecule. Okay, so this is like why salt is able to dissolve in water, because the sodium ions and the chlorine ions, those are attracted to the water, right? So it's an ion that's attracted to a polar molecule. So that attraction is what causes the salt to actually break apart and become dissolved in water itself. Okay, so that's an ion-dipole interaction. All right, so now dipole-dipole. In order for a dipole-dipole attraction or force to happen, you have to have polar molecules. Now, it doesn't have to be the same polar molecule. They can be two different polar molecules, but they're attracted to each other, okay? And just like we always know, a negative is always attracted to a positive. So the negative end of one polar molecule is going to be attracted to the positive end of a different one, okay? Now, obviously, these are only important when the molecules are close enough to each other, right? So in liquids and solids, that's when you're going to see these dipole-dipole interactions. You're not really going to see it a whole lot with gases because they're spread apart further and they're moving so much. So this is kind of like when we talked about on Thursday with your gas molecules and stuff. If they're moving slower, then they'll be able to attract each other. But otherwise, they're kind of off doing their own thing. All right, now, the more polar the molecule, the higher its boiling point. So why would that be? Because you have a stronger attraction to each other, okay? Oh, whoops, I went too far. There we go. Because we have a stronger attraction to each other. So this is where, like, you can have, let's see here. You can have these dipole moments. Now, they're increasing here. And so their boiling point is as well, because the more polar something is, that means it has a stronger partial positive or a stronger partial negative. Okay, so think of it as like a stronger magnet. All right. Okay, so London dispersion forces. London dispersion forces are a little weird. So let's see here. This is the one I want to look at. Now, if you have a helium atom, right? Now, we know that helium is nonpolar. It's a noble gas. It's not really doing much. If you put it next to a polar molecule, then what happens is this negative here is going to force these electrons off to this side, right? Because remember that negatives repel each other. So if this negative is here, it's going to push these electrons off to the left. And when that happens, it creates a partial negative for a split second of this helium here. And then when that happens, then it causes another helium atom to end up with another partial charge. Okay, so it's called induced dipole. So basically, this helium atom would look like this one, where the electrons are just spread apart. But because of this guy, it forced the electrons to go off to one side. So it's forcing the electrons. That's why we would call it an induced dipole. Okay, so like when they say that, when a woman's giving birth, they say they might have induced labor. Like they're kind of pushing it along to force her to have the kid. Okay. So there we go. So London dispersion forces are attractions between an instantaneous dipole and an induced dipole. Okay, so the induced dipole would be here. The instantaneous one would then be here, because now this one is also forced to become attracted to this guy just kind of randomly. And when we say instantaneous, it just kind of happens. It's not permanent. Okay, that's why London dispersion forces are so weak. It's because you have these temporary dipoles that just kind of happen all of a sudden, but then it goes away real quick, and then it happens again, and then it goes away real quick. So it just happens over and over and over again. And then, oh yeah, these forces, they're in everything, right? Doesn't have to be polar or nonpolar. It's just that they're the most important in nonpolar because it's the only force that nonpolar molecules have, okay? Now, this is a huge word right here, polarizability. All it means is that the more electrons something has, the more polarizable it is. All right. So let's say we were talking about F2 gas versus Cl2 gas. Okay. Now chlorine has a lot more electrons, so that means it's more polarizable. It means that it has more of these electrons that could be distorted and pushed off to one side. Okay, so because it's more polarizable, that means it's going to have more London dispersion forces, and so it's going to have like a greater boiling point. The London dispersion forces are going to be stronger, basically. Okay. Now the shape of the molecule also affects the strength of the dispersion forces. So a long skinny molecule is going to have stronger dispersion forces because there's more surface area. Okay, and that's the important thing, is you want more surface area because that means that the electrons are all on the outside, so they can be distorted easier. Okay. Let's see. The strength of dispersion forces also tends to increase with increased molecular weight. So like here, molecular weight is increasing, the boiling point is increasing. Okay, and that's really just because the bigger those molecules are, they have a larger electron cloud, right? They probably have a lot more electrons, which means they're more polarizable. Okay? Remember to use that word. Now, if two molecules have the same size and shape, or they're similar, then your dipole-dipole interactions are going to be the dominating force, okay? If one molecule is much larger than another, then the dispersion forces are going to determine its physical properties. All right. So basically what that means is if you're dealing with let's say HCl versus HF, well, they're similar in size, and HF is going to have your hydrogen bonds. Okay. Now, if you were talking about two molecules that were way different, so let's say I was dealing with HF versus I don't know, C6H12O6 or something like that, right? A much, much larger molecule. That one might end up with a lot more dispersion forces, so it could have a higher intermolecular force, or could have stronger intermolecular forces just because it's so much bigger. which means that like even though this one has hydrogen bonds and we know that those are stronger, overall they might be weaker. All right, so now moving on to hydrogen bonds. Hydrogen bonds are only when hydrogen is attracted to a nitrogen, oxygen, or fluorine, okay? We say that they're hydrogen bonds, but they're not really bonds, right? They are just forces. They are just attractions. Whoops, okay. So here is a big part of hydrogen bonds. The hydrogen has to be attracted to a nitrogen, oxygen, or fluorine, but it also has to be polarized by a nitrogen, oxygen, or fluorine. Okay, so here's what I mean by that. Notice how here you have these attractions, okay? This hydrogen, these red hydrogens here, were all polarized by a nitrogen, an oxygen, or a fluorine. Now, if I were instead to make this, let's say this was, I don't know, phosphorus instead, okay? That's ugly. But let's say if that was phosphorus instead, this would no longer be a hydrogen bond, okay? Because that hydrogen was not polarized by a nitrogen, oxygen, or fluorine. That would just be a normal dipole-dipole interaction, okay? Hopefully that makes sense. Yeah, you guys know this. All right, so here's kind of to sum it up. All right, if you guys want to take a picture of this or put this in your notes, it might be helpful, but just know here you've got your dispersion forces, dipole-dipole, hydrogen bonding, ion dipole, which is a new one for you guys, I think, and then you have your ionic bonding, which we call it a bond because it's very, very strong. But it's still just an attraction between two ions, right? A positive and a negative, and that's it. All right. Hopefully this all made sense to you. You guys need to grab the worksheet titled Intermolecular Forces from the sub, and then you guys can work on that. When you're done, check the answers. I left the answers with the sub, and then you guys can work on your online homework. Okay? Have a wonderful day, and I will see you on Wednesday. Bye.